For years, astronomers had an embarrassing problem. When they tried to count all the ordinary matter in the nearby universe, the numbers did not work. Not dark matter, not some exotic new substance. Ordinary matter. The atoms built from protons and neutrons. The material in stars, planets, gas clouds, your body, this room, and every familiar object you have ever touched. The universe seemed to be missing a huge amount of it. And the strangest part was not just that it was missing, it was that we already knew with surprising precision how much there should be. That is what made this so unsettling. The total was not the mystery, the inventory was. Depending on the census and the method, something like a third, and at times closer to half, of the ordinary matter in the later universe was not showing up where astronomers expected to find it. Then, whenever the search improved, the answers seemed to shift. First, the missing matter looked like it should be in galaxies. Then around galaxies. Then between galaxies. Then in hotter gas, thinner gas, more diffuse gas. It kept changing address. That is the missing baryons problem. And to understand why it became such a stubborn puzzle, you have to start very early. Not with galaxies, not even with stars, with the first few minutes after the Big Bang. Back then, the universe was hot, dense, and simple enough for the basic nuclear bookkeeping to be unforgiving. Hydrogen and helium began to form in proportions that depended very sensitively on how much ordinary matter existed at the time. Change that amount, even a little, and the ratios come out differently. Much later, the cosmic microwave background preserved another independent record of the same underlying baryon density. Those two lines of evidence, early nuclear physics and the oldest light in the universe, turned out to agree remarkably well. So cosmologists were not guessing. They were not working from a vague estimate. They had a number. Then they looked at the nearby universe and tried to count the atoms. Stars only gave part of the answer. Cold gas inside galaxies helped, but not enough. Dust added a little. Hot gas and galaxy clusters added more. Even after all of that, the census still came up short. So where was the rest of it? The obvious place to look was the space between galaxies. That sounds empty, but it is not empty. Galaxies live inside a much larger environment. Gas threads through the universe on enormous scales. The first thought was simple enough. Maybe the missing matter was sitting out there as relatively cool, neutral gas, faint but detectable. That did not solve it. Then the picture changed. Maybe the gas was not cool at all. Maybe it had been heated up as cosmic structure formed. That idea made physical sense. Gas falling into the growing web of matter does not drift in gently. It gets pulled, compressed, shocked, and stirred. Some of it is heated to extreme temperatures. Once that happens, hydrogen loses its electrons and becomes ionized plasma. And ionized gas can be very hard to see, especially when it is spread thin across immense distances. So the suspected hiding place became what astronomers call the Warm-Hot Intergalactic Medium. Vast reservoirs of hot, diffuse gas stretched through the cosmic web, mostly between galaxies. Too thin to glow brightly, too ionized to show up the easy way, and difficult to pin down with any single instrument. That was a serious step forward. It explained why the missing matter might be real and yet frustratingly hard to detect. But it did not end the problem. It just moved it into a more difficult form. Astronomers began looking for fingerprints. One of the best tricks was to use quasars, the brilliant cores of distant galaxies, as backlights. When their light crossed thin gas along the way, that gas could leave tiny absorption features in the spectrum. Those features were subtle, but they mattered. They showed that at least some of the missing baryons really were out in this diffuse medium. Still, the accounting did not close cleanly. And around the same time, another complication became impossible to ignore. Galaxies are not sealed containers. They form stars. Stars explode. Black holes feed and erupt. All of that dumps energy into surrounding gas. Some of that gas gets pushed far from the visible galaxy into a vast, tenuous halo. That region is called the circumgalactic medium, and it turned out to be much more important than earlier pictures had suggested. So now the missing baryons had, apparently, moved again. Some were still thought to be out in intergalactic filaments. Some seemed to be lingering in enormous halos around galaxies. Some were probably in hotter phases than the measurements were sensitive to. Some were in environments where one technique could see them and another could not. This is the point where the story gets especially interesting, because the matter was not only hard to detect, it was also cycling through different states and locations over cosmic time. Gas falls toward galaxies. Some of it forms stars. Some of it is heated. Some of it is blown back out. Some of it stays bound in halos. Some of it escapes into the larger web. So the missing baryons were never sitting in one neat vault waiting to be discovered. They were part of a moving system. But there was another reason the location kept changing, and this part matters just as much. Our measurements kept changing too. Each method could only see one slice of the total picture. Ultraviolet absorption worked for certain gas. X-rays helped with hotter material. Other techniques were sensitive to clusters, or stacked halos, or particular ionization states. Every new approach filled in one part of the map and exposed how incomplete the old map had been. The baryons were not playing hide and seek. We were doing a partial census with incomplete tools. Then came one of the cleanest breakthroughs in the whole story, from a source that seemed almost unrelated at first: fast radio bursts. These are brief, intense flashes of radio waves from far outside our galaxy. They last only milliseconds, but they carry an extraordinary advantage. As the radio pulse travels through ionized gas, lower frequencies get delayed more than higher ones. By the time the signal reaches Earth, that delay contains a record of how many free electrons the burst encountered on its journey. That turns the universe itself into a measuring device. A fast radio burst does not show you a pretty image of hidden gas. It does something better. It tells you how much ionized material the signal passed through. And that changed everything. Once astronomers began using well-localized fast radio bursts, they could finally weigh the diffuse matter spread across intergalactic space in a much more direct way. First, those measurements showed that the missing ordinary matter was not gone at all. It was really there, largely in ionized gas. Then, larger samples began to sharpen the picture further. The emerging result is striking. Most of the universe's ordinary matter appears to live between galaxies, in the intergalactic medium. A smaller, but still important fraction sits in galaxy halos. Only a relatively modest share is locked into the bright, obvious parts we notice first: stars and cold gas inside galaxies. That is a profound reversal of intuition. When we look at the night sky, the bright structures feel like the main event. Galaxies look like the places where the matter is. But the modern picture suggests otherwise. The luminous parts are the minority. Most ordinary matter is dispersed in the dim background, stretched through the web that connects galaxies to one another. So, is the missing baryons problem solved? Mostly, yes, if the question is whether the matter exists. Not entirely, if the question is how that matter is distributed, how it moves, and how violently galaxies have been throwing it back into space. That is where the problem has matured rather than disappeared. The old version of the mystery was, where are the missing baryons? The newer version is, what does their final distribution tell us about galaxy formation, black hole feedback, cosmic heating, and the way matter circulates through the universe? Because once you realize that most ordinary matter is not sitting in stars, the story of a galaxy changes. A galaxy is no longer just a shining island of matter. It is the visible knot in a much larger flow. Matter comes in. Matter gets heated. Matter gets expelled. Matter drifts through halos and filaments and may later fall somewhere else. And that is why the missing baryons kept seeming to move. Partly because they really do move, through a long cosmic cycle. Partly because we kept learning to see a different phase of the same material. And partly because the universe does not arrange its matter in the places human intuition prefers. Not in the bright center. Not in the obvious structures. Mostly in the faint, extended medium between them. What looked like a missing matter problem turned into a lesson about perspective. We were staring at the lit windows and forgetting the city around them. If you want to go deeper after this, there are a few carefully chosen books in the description that do exactly that. And if this changed the way you picture the large-scale universe, the videos on your screen continue from here.